this is for Open Up Algebra 1, Unit 1, Lesson 1. And my goal for these videos is for students and teachers to be able to watch these videos and feel confident about getting into this lesson or to review this lesson. In these videos, I plan on sharing some of my strategies for learning the material as well as some teaching strategies. I am likely going to focus on learning strategies since it will be students learning this material. I'm sure that teachers watching these videos might also benefit from this style. So, for our first lesson of Unit 1 on arithmetic and geometric sequences is this lesson on checkerboard borders. Okay, so we essentially have a checkerboard pattern here, and we always are going to see this. In this case, it's a 5 by 5. I guess white space, right? So we have this pattern of tiles shown by a 5 by 5 square of white tiles surrounded by a border with alternating colored squares. Show how you would group the tiles to quickly count the number of colored squares in the pattern. So essentially, we don't want to sit here and individually count these green squares. We want to find a generalized pattern of equal. So we want to find groups that have equal size, so we can quickly count the number of squares. So lots of students really fall under four main categories. So the first one that students normally find are these two groups, and then these on the sides. So that has 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 times 2, and then we have 1, 2, 3, 4, 5, and then 5 times 2. And where am I getting the times 2 from? It's from the two groups. So that's one category. So another category that students will fall under is they might fall under this category here. They'll see, oh, the corners always have 2 green squares, and then they'll see these groups that are left over all have 5. So they'll think, oh, okay, so that's 2 times 4, those are the corners, plus 5 times 4, those are the blue squares. And they'll quickly count them that way. Another pattern you might see as a teacher or as a student is you can take the area of the entire square, right? And so that's a 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a 9 by 9 square. Take away the 5 by 5 square on the inside. So that's 81 minus 25, which is equal to, I believe that is 81 minus 25. Okay, carry the 1. That's a 9. Oops. And then, so it's 81 minus 25. Should be 30. Well, let me think about this problem for a second. We are going to need to eventually divide by 2. So we get 56, and then we'll need to divide that by 2. for every other square. Yes. So we get 28. That's 28 total green squares. So that's another pattern. And the last pattern that students might see is we can actually cut this graph into corners, and we see that each corner has 1, 2, 3, 4, 5, 6, 7 in each piece, which gives us 28. So those are the main camps that students will fall into. So the goal, though, is for students to find their pattern that they like and to hold on to it for the entire lesson. This is going to help them generalize the pattern. If you're a student, when I say generalize the pattern, I mean this is going to help students be able to come up with an equation for their pattern. So so for our lunch, in preparation for going back to school, the school administration plans to replace the tile in the cafeteria. They would like to have a checkerboard pattern of tiles, 2 rows wide, to surround the tables and the serving carts. Let's get into our Explore. So our Explore is our first question. So here's the same exact pattern, except now we have a 6x6 in the inside. And so with students that struggle, if you're a student you struggle with finding a pattern, I always say actually start with finding the area of the whole square. So we're going to find the area of entire square, which in this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a 10 by 10 big square, and then find the area of inside white space. That's a 6x6. And of course, to find the green squares, we need to do that 10 by 10, which is 100, take away 36. So that leaves us with 64 total squares. We need to be careful though, because we don't want total squares. We're looking for just the green squares, and we see that it's every other tile. So now that we essentially currently have all of this counted. That's 64 squares, but we need to cut that in half. We need to cut that in half, divide by 2, which is 32 green squares. So I like to hold on to this strategy for the rest of the lesson. This is what I ask students to do. I'll also ask students to share their ideas and maybe compare strategies, but for their own personal work, I want them to hang on to the strategy that makes the most sense to them. And so this is the crux of the entire lesson, right? So we want to use the same counting strategy that we used before, except now we have an n by n interior area here that could grow, right? It could be any area. And the goal is for you, the student, or you, the teacher, to be able to take that counting strategy that we used in the previous 2 questions and apply it to this question. So we essentially have this exterior area that's still every other square is green, and don't fall into the habit of trying to fill in some squares here, right? We don't know how many green squares there are going to be that we can fill in. We do know, however, that they will alternate. They will continue in the same pattern. Okay, so we want to continue using the same counting strategy. So like I always tell students, let's find the area of the big square, take away the area of the little square. We know eventually we're going to need to take away an area of n by n, and students typically find this. And we know eventually we're going to need to divide by 2, and that's going to equal green. However, it's the area of the large square that students really tend to trip up. So what I like to do is I like to have them agree first that this side, this edge, that is n. we need to agree on that is length n. And then we also need to agree at some point that this orange area here is worth 2. It's worth 2 squares on each side. So this entire length that I'm going to put in pink now, this entire length has to be called, if we add everything up, n plus 4. It's length n plus 4. And similarly, this edge would also be n plus 4 because it's a square. So we have n plus 4 times itself plus, take away n by n here, and then divide by 2 to find green. And students, you can stop here. You can leave your expression as n plus 4, take away n to the second power, divide everything by 2, and that's going to equal green. Just don't forget you need to find this and then divide by 2, so we're going to put brackets around that. And we could simplify this a little bit, but we don't need to at this point. We don't need to at this point. So this is one counting strategy. Another counting strategy that you could work on is, let's say you really, really liked the counting strategy where we had 2 rectangles on the top and the bottom, and then 1 rectangle here and here. Well, we need to also see that this length is also n plus 4, and this length is 2. And we have 2 of those, right? So we're going to do n plus 4 times 2 times itself, because we have 2 rectangles, top and bottom. And we also need to add this length n times 2, or 2n. And we have 2 of those, so we need to square. And then we need to divide everything by 2, because we want to count only the green squares. Well, if I simplify that, I'm going to get the exact same expression. And that's the point. The point is you can use any strategy, any counting strategy, and you will always arrive at the same expression. You might need a little bit of simplification, but you will arrive at it. So some takeaways for our first lesson: use color, use highlighting, use groups, right? Equal groups to make your thinking visible. Notice the number of groups and the size of the groups. That's important. If their groups aren't the same size, then we can't use that to write our equation. Look for quantities that are changing the same and that are changing. Look for quantities that are changing and quantities that are staying the same. And use areas, right? Use areas, especially of rectangles and squares. And so lastly, I want to do our exit ticket. So assume that each of the squares below is 1 by 1. So this is a 1 by 1 square. Write an expression for the perimeter of the rectangle made up of n squares. So this is my favorite explanation. How long are each side highlighted in pink? They're 5. And this is 1. So to find the area, so find the perimeter of the rectangle, we have 2 groups of 5 plus 2 groups of 1. So that's 10 plus 2, which is 12. So if we count these, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our expression works. However, let's say that this this is worth n squared, so this would continue, right? Well, this length would always be 1, and so would this one. But what's going to change the same is this pink length here. if that continued, right, this length needs to be called n. We don't know how long it is, but we know it's worth n. It's n squares. So again, we still have our two groups of 1, that didn't change, plus our two groups of n. If we can simplify that, that's 2 plus 2n. That's our perimeter. Okay, so I'm going to try to keep these short. Some vocabulary, we'll just wrap this up. Equivalent equations, right? Depending on what method you use to count your number of green squares, no matter what generalized equation you came up with, you'll always end up with an equivalent equation. And equivalent expressions, essentially a similar definition, except there's no equal sign. So I'm going to wrap it up here. Hope you found this helpful. Please feel free to leave a comment if you have a question. I love discussing this lesson. It's my favorite lesson to start off the year. Start off really every year. So thanks again for listening, guys. See you later. Bye-bye.